Of course, the big application of cross products is torque. So, which is the idea that we use to motivate cross product in the first place. So, to find the torque vector, because it is a vector, remember down the bolt or up the bolt, we place the origin at the point of rotation, i.e. the bolt or the hinge. We let P represent the point at the end of the lever wrench that you're pushing on. Let R, the radius, be equal to the distance, or the vector, from the origin to P, point P. So let me see if I can show you all of that. So R is from the origin right here to the vector P, so at point P. So over here, there's point P. Over here, there's the origin. Right? Okay, so the radius goes from the origin, O, to P, the point P, right, where you're applying the force. All right, so the force applied to the lever has a force factor, right? And then theta is the angle between the radius and the force factor. So the radius vector and the force factor. So you can see theta right there. And then the torque vector, tau, is r crossed with the force, right? And so the magnitude of that torque is equal to the magnitude of the cross product. So the torque vector is that way. So torque is right here. So this vector right here is the tau vector, torque. That's this vector going that way. Here, I'll use a little highlighter so you can see. So the torque vector is right here, following the right-hand rule. Right, so that's how to find torque. All of that. Very important definition to know. Okay, now before we quick and do a torque problem, let's just real quickly notice that because this is force times a distance, the radius vector is a distance, it's going to actually have the same units as work, which is Newton meters or foot-pounds, depending on which system you're working in. All right, so let's actually do one. We have a pump handle works by rotating about a pivot point. For a particular pump, if the pivot point is at the origin, the end of the handle is at 0, 6, negative 20, distance measured in inches. When someone releases the handle, a force in pounds of F is applied. Oh, someone raises the handle, sorry, not releases, so they're lifting it. So here's what's happening. You have your origin right here at that point right there. And what you're doing is you have your radius vector coming down this, right? So there's your radius vector to this point down here, and the point down here is point P. And P, they tell us, is at 0, 6, negative 20. Right? So, which makes sense because the origin's over here. That's 0, 0, 0. And so we've gone 0, 6 over 6 down 20, right? We haven't gone back into the paper at all. So that's why your x is 0, right? This is essentially being treated like a two-dimensional thing. All right, so r would be the vector from the origin, which is 0, 0, 0, to p. So this is 0p, not 0p, OP. O being the origin, P being the point that we go to. That's the vector between the two. Terminal minus initial would mean that this vector is 0, 6, negative 20, all in inches. All right, sure. And then you're applying a force because you're raising the handle. You're going to lift it up. So your force vector comes in like this, right? Force vector, like that. So you're going to lift your force, right? And they say that the force that's being applied is 0, 3, 0, 3, 10. Okay, so then what's the torque? The torque will be the cross product between the two. So I'm going to have to put that down here. So tau would be equal to the cross product of I, J, K, of my two vectors. It'll be my radius vector crossed with my force vector. So my radius vector was 0, 6, negative 20. My force vector is 0, 3, 10 because they told me so. All right, now to do the quick little method, I'm going to add in an extra 0 and a 6 and an extra 0 and a 3. I'm going to take the cross product. So let's see here. Oh, you know what? To make this all go better, there we go. All right, so let's see here. I'm going to go on the diagonal right here. I goes with 6 and 10. So that's 60I plus 0j plus 0k. Nice. They all disappeared. Minus. And then I'm going to go the other direction. So that would be 0k minus 60I. And then 0j. Interesting. So you might be thinking, oh, they canceled out. Oh, they did not. 60 minus a minus 60 is 60 plus 60I, which is 120I. So your torque vector, tau, is equal to 120, 0, 0. There's the torque vector. All right, now the magnitude of that torque vector, the size of it, is equal to the square root of 120 squared plus 0 squared plus 0 squared, which is rather minute, right? So that would be, I mean, these all disappear. These are minute, so as in they don't exist. And so therefore it's just 120. And this would be inch pounds, right? Because they gave it to us in inches and pounds. Interesting, right? Because they said the force, actually I should have mentioned that up here. This is in pounds right here. So this was in pounds, the radius was in inches. So when I get down here, I have inch pounds. Now what would that be in foot pounds? Well, I would multiply by, for every 1 inch, or excuse me, 12 inches for 1 foot, right? So I want the inches to cancel, so I put that in the denominator, and then I'd multiply. So I'd end up really dividing, right? 120 divided by 12, which would be equal to 10 foot-pounds. So if you want it in the most common American measurement of torque, that's what it would be, 10 foot-pounds. Now what about the direction? The direction would be right, so find the torque, find the direction. Okay, so the direction is heading which way? So we're taking our force, we're applying it this way. So if you curl your hand, right, take your hand, and you take your radius and you're pushing against it. Oh, sorry, I can't twist my hand that much. So you have your wrist at the origin, you're curling your fingers this way because you have your radius and then you're pushing along it with your force. You can see that the torque is coming up this direction. So you're heading in the positive x direction since this is y and that's z. So we're heading in the positive direction. So the torque, in other words, it's moving out at us through the screen, right? The bolt is coming out this way. So the torque is heading from the origin up into the air in this particular case, right? But that direction is east. Just to make sure you understand what's happening here. So what's happening is if that's the origin 0, 0, 0, and this is 0, 6, negative 20, that's 0, 6, there's the y direction, there's negative 20, that's the z direction. So we've kind of made it so that this is the y-axis, and then That's the z-axis. So the torque has nowhere to go but up based on the right hand rule, because you put your wrist at the origin, you put your hand along that r, that radius vector, and you move it, you curl it based on the force. So it goes this way, and so therefore the torque is going up the bolt. And that's the positive x direction, since that's the y-axis and this is the z-axis. The x-axis is actually coming straight out the bolt, right? And that's what I mean when I say the positive x direction, right? It's coming straight out towards us. Let's do another application of torque before we move on to a different application of cross product. So you adjust the screen on your laptop by pushing on the cover. Everybody's done this. I've seen students do this all the time. With a force of 8 newtons at a distance of 18 centimeters from the hinge. If your hand is at a 42-degree angle to the screen, find the magnitude of the torque applied. So you're adjusting your screen by pushing on the cover, right? Let's see here. If your hand is at 42, so they're telling us that a force, if you see this right here, there's your force vector. And you know that the magnitude, well, it's not the vector, but you know that the magnitude of it is 8 newtons. That you know. And then they're also telling you that you have a distance of 18 centimeters from the hinge. So they're telling you that the magnitude of r, the magnitude of your radius, is 18 centimeters. Right? Which would be 0.18 meters if you think about it, because centimeters is per 100, right? So hundredth of a meter. So you'd move the decimal 2 spots over to get to meters. All right, so then the magnitude of the torque vector is r crossed with f. Magnitude of r crossed with f, which we happen to know by definition is r, the magnitude of r, the magnitude of f, the force, times the sine of the angle that's between them. That has to go back to the definition right here of the magnitude of torque, right there. All right, well, they gave me all the pieces I need for that. I know that the magnitude of my radius vector is 18 centimeters, or 0.18. Either way will work. It'll just change my unit at the end. And then the force vector was 8, right, newtons, times the sine of my angle. But my angle is right here. They're telling me that theta is 42. So 42 degrees. They didn't actually want the vector. They just want the magnitude of this vector. So you'll notice, since all they want is the magnitude, this is an easier problem than the one we just did with the water pump. So you multiply these three, and you'll get 96.35. Now that would be Newton centimeters, of course, because the pink one was in centimeters. Now if you wanted to use meters instead, it would have been 0.9635 Newton meters, which is also known as joules. They didn't specify which units they want, so any one of those three would work. That is the amount of torque going down the hinge. And if you were going to design laptops, you would want to make sure that your laptop could withstand such amounts of torque, which I'm sure it could.